So hi everyone, I see many familiar faces in the audience. So let's start. You've heard this over and over again, but let me share this with you again. So the whole technical advancements in this GenAI space have really exploded in the last couple of years, and innovation is continuing at this really rapid pace. So based on this recent study, we see that about 80% of enterprises will have GenAI by 26. 50% of edge deployment will also have GenAI. And while there is so much excitement and hype around this, but in reality, we are only seeing about 10% of organizations in production deployment today. And as we talk to experts in this space, and while they really want to use it, they are citing infrastructure as the big barrier to adoption. They really don't know how to go about deploying it on their on-prem infrastructure for the enterprises. And the biggest issue is these language models are really, really huge. So that's one big barrier. The second barrier is around security and privacy and trust. And so I will focus on these two barriers in the rest of my talk to see how we can mitigate these barriers. So clearly, we've also heard this several times in this conference today, that the model sizes continue to grow. So the chart here is only listing some of the open source models, and really we do need to increase the model sizes to get the performance that we want out of these. And but enterprise data centers can't really scale to train the models of these sizes. So if you look at from OpenAI, the GPT-3 costed about $10 million, GPT-4 about $100 million, and now they're already beginning to train GPT-5. So you can take a guess how much that will cost, and I think they're talking about billions of dollars, right? So clearly we need to have nimble and efficient models. And it's not a new problem. As I said, you've already heard this, and it's a recognized problem. So we are actually seeing these nimble models emerge, which are like 10 to 100x faster to run than the giants. And then some of them, actually, if you look at this chart, there is Mistral 7B that's supposed to be much faster, but has the same performance as Llama 33 billion. This is based on a study I'm quoting here. So with these nimble models emerging, they're actually being used as foundational models. So which means the enterprises don't have to train these models from the start. They can start with one of these open source foundational models and then train them on their private data. And this is a very, I guess this is the trend that's emerging right now. So in addition to these smaller model sizes, so by the way, machine learning community is extremely active right now, and they are looking at more and more efficiency techniques. So I'm listing a couple of those here. So one of them is this model compression technique, where you can reduce the accuracy of these models. Oh, sorry, you can use the lower precision without losing the accuracy. And then there is another technique called model pruning. So these deep neural networks are extremely dense, and you don't really need all of those connections. And there are techniques where you can remove some of those unnecessary connections to again reduce the model sizes by 10x. So 10x with quantization, 10x with classification, so you can almost get 100x reduction in data sizes, which means now you can run these models on, you can say, reasonable hardware. You don't need GPU farms to be able to run. The training is a different story, but I'm talking inferencing here. And good news is, it's not just these two techniques. So I tried to go look for what else is machine learning community doing. So it just doesn't fit on a page. There's so many techniques that are in play. Clearly, community is working towards these nimble and efficient models to make it a reality. So with that, now that you can run these models on existing systems, and a lot of these enterprises deploy Intel Xeon platforms. And so not only that you can run these on Xeon platform actually comes with now this, what we call as advanced matrix acceleration. So it's a CPU extension where it gives you a bunch of new instructions to be able to do these faster matrix multiplication operations. So there is a set of tiles and which can hold lots of data, and a Nimble engine which can do these operations on this for matrix multiplication, which is a very common operation for these deep neural networks. So there is a chart here that basically shows 10x better performance over previous generation, which uses AVX 512. So AMX is already showing 10x improvement over our previous gen hardware. So yes, so with that, imagine if you had a data center with Xeon platforms already deployed, and now you have these foundational models. How can you use them for your business operations? So there are a couple of techniques that enterprises are using. The first one, again, I think you've heard several times in the conference today, is this technique called retrieval augmented generation, RAG. So here, basically, you don't retrain the model. You take the foundational model, and if you have your enterprise data, you can ingest it into a vector database, and when you query the model, you also give it the additional context from your private data. So model can actually give you answers based on your private data. But in this case, the model remains the same. You don't really change the model at all. And in the second technique, sometimes actually RAG works great for some of applications. Other applications, it doesn't work so great. In which case, you have this technique called fine-tuning, which means you do bring in a pre-trained model, which is already sort of trained on a large amount of data, and then you can train it or fine-tune it on your data, in which case you directly query the model, but really you are skipping this task of training a complex model. So with this, nimble and efficient models, you can actually run these models in your enterprise already with these two techniques. But so that's the first problem. But what about security and privacy and transparency concerns? Because I think that's a bigger barrier that many enterprises are facing. So again, this morning, we actually heard Dawn talk about quite a few attacks on the AI pipeline. But if you look at this AI deployment, the pipeline has several steps, and an attacker can really has several opportunities to attack this pipeline. Of course, we have heard all throughout you want to protect your model IP. So there is this attacker can steal your model IP either during training or during inferencing, and your data, even during training, the data can be either stolen or can be mislabeled, resulting in sort of bad results from your models. And even during inferencing, there are lots of attacks around model. They can extract the data, or they can just sort of gather intelligence about your model parameters through queries and such. So this is only some attacks, but there are quite a bit of attacks that are possible throughout the pipeline. So what are we doing to address these attacks? So we're looking at roughly, I've divided them in 4 categories. The very first one is clearly we need, if you want to protect model IP and data, you need confidential and verifiable workflow. Meaning you want to make sure your data remains protected, and you can actually verify that you're exactly using the model that you're using. But that's not enough. I mean, that's just a small part of it. How about privacy concerns? Like even if because many people will tell you confidentiality is not privacy. So we have to have some additional algorithms in place to be able to guarantee privacy. For example, differential privacy, and I think Dawn talked about that also this morning. There are issues around provenance. Do you know the model was trained on the right data? Was it, so to be able to, because model goes through training and retraining, and you want to be able to trace that back all the way to its origin. And then access control. So now in your organization, if you train the model on your private and sensitive data, and you don't want anybody to be able to extract, say, your salary data of all the employees, you have to make sure that access control that was maintained on your documents or data still remains maintained when you're using GenAI. So confidential computing is a great foundation to address confidential and verifiable workflow. Actually directly addresses the first one. But for everything else, it provides a nice foundation, because then you can build techniques or algorithms on top of confidential computing to be able to get privacy, provenance, and access control. And we're doing a lot of work at Intel in both labs and otherwise to take care of these problems. Okay. Actually, I had a slide just for completeness. Everybody here knows what confidential computing is, and you know it's for its protection of data in use. Quickly, just to say it by performing computations in trusted execution environment. And for those, just in case you didn't know, a TEE is an area that allows hardware to create an area in the processor memory which isolates from rest of the software, and it also gives you encryption through confidentiality through encryption, and it also provides a technique called attestation for verification. Intel has two such technologies, Intel SGX for app isolation and Intel TDX for VM isolation. Intel is actually unique in this, that we are the only ones who provide app isolation. Pretty much all hardware vendors provide these confidential VMs via VM-based isolation. So let's go back to our enterprise deployment scenario, where I showed you that they can deploy RAG. So in case when you're deploying RAG, you're deploying on-prem. So you may ask, why do they need confidential computing? We also heard about this big problem around insider attacks. So that insider attack is not only a problem in cloud, it's also a problem in big enterprises. So if you are, first of all, you have sensitive and private data, you want to make sure it's protected from everybody, and you can only access it if you have access to it. So protecting that in a confidential computing environment will give you that benefit. When you're using a foundational model, the model is already open source. So truly you don't need the confidentiality, but you do need the integrity. You want to make sure you're exactly using the model that you wanted to use. And in case of fine tuning, again, the model has your sensitive IP. It's your model parameters are basically tied to your data. So you want to make sure that you run it in a confidential compute environment, both for confidentiality and integrity. So with these technologies, the enterprises can have Nimble models via foundational model deployed, and they can be protected with confidential computing. Okay. So while this is all great, like I mentioned, the Nimble models are here, and you can run them on today's systems. You can actually protect the model IP and data using confidential computing. But really, there are several challenges around this. We want to make sure that you don't lose the performance, because I think in the AI space, the performance is a big factor. The moment you throw them in TEs, can you still get the performance that you were getting? How much of an overhead people are willing to accept with these confidential VMs. And no matter what, even on enterprises, you're running these heterogeneous environments. You're running CPUs, but you're also running GPUs or other accelerators. And then, in addition to these small models, when you're running the larger models, you will be running them in this heterogeneous multi-node clusters. So not only you want to secure the CPU to GPU connection, you want to also be able to support the scale out. And the last but not the least, you want to have this end-to-end integrity assurance for traceability and verification. We talk about attestation, which is sort of a tool to achieve this, but there's a lot of work that we have to do to achieve that. So with that, like I mentioned, we are working on all of those areas. So the very first one is we were looking at these performance optimizations on various GenAI models. So we did some experiments with the Llama 2, and basically we ran this Llama 2 model with and without TEs. And I have some data showing here. Effectively in this space, you look at what is your second token latency, because the first token is always very expensive. And as we looked at the second token latency for width, and so we ran it for all different precisions. With AMX, it's basically running on bfloat 16 and int8, and we also have the data for FP32. But if you really look at TDX and no TDX, we basically are getting less than 3% overhead when we are running the Llamas. This was the 7 billion model, but we have also run the 13 billion and 70 billion models. Also, you've already seen several RAG demos. I also have a RAG demo. RAG demo was actually done on Llama 13 billion. So on the left-hand side, I'll just show you a video. On the left-hand side, we have a Llama running in a normal Xeon. And on the right-hand side, with basically the standard Llama 13 billion, on the right-hand side, we gave it some additional data about Intel Labs via RAG vector database, and we ran the whole thing inside a TD along with the RAG database. I want to show you that while we saw that 3% overhead, for a user visually, you really don't notice any difference. So we asked the model, sort of introduce yourself, and in both the cases, it basically gives you a standard answer that I'm a Llama model. But then we go and ask, can you tell us the confidential plans of security and privacy lab? On the left-hand side, it says, I have no idea. But the right-hand side, it gives you a more intelligent answer that the labs is working on the secure AI, ML, and few other notes on it. But if you visibly notice, you didn't really notice any difference. 3% overhead, second token latency is almost unnoticeable in the GenAI scenarios. Yes, I guess built there. That was the answer coming from TDX model. Okay, so shifting gears a little bit, like I mentioned, the GPU, and you've heard a little bit today about extending the confidential computing to the accelerators, and Intel also has plans to support TDX Connect. It's basically a standards-based approach. It's built on the standards that we also heard earlier today, like TDISP, ITE, and SPDM. So good news is, because it's an industry standard, devices can support these industry standards, and different CPU vendors can sort of work on getting their CVMs working with the devices that support it. And once you can have this connection established, you can directly DMA into the TD memory. You don't have the overheads of bounce buffer and such, which those are the solutions that we are deploying today. If you look at specifically for GPUs, what we have today. So like I mentioned, CPU-based confidential AI, you can actually run today, and you can do a lot. That's what I showed you, especially with these Nimble models. But when you do want to run models that are running in this heterogeneous environment, Intel TDX already works with NVIDIA GPUs. And in the phase 1 with H100, it was mentioned quite a bit today, you can use this bounce buffer solution. But once TDX Connect is available, then we will get rid of all of those performance overheads, because it comes at a cost today. So with that, effectively, the message to this audience is that enterprise GenAI can really use these foundational models, and then it can use fine-tuning or RAG to be able to deploy their models on Xeon platforms with the AMX accelerated hardware. And then you can combine it with confidential computing with TDX or SGX, because we can run all of these models in SGX as well to get the security and privacy benefits. But my last slide, we are not done. We actually have a lot of work ahead of us to make it a truly end-to-end deployable technology. The first one is my summary, where you can run these Nimble and confidential models. But really, we have to secure this whole pipeline from data sourcing to deployment. So we are already beginning to do this work, and there is some work happening in C2PA, which is an industry organization. It started as content protection. They have these provenance controls. And now that C2PA is also looking at protecting AI pipelines. So you can specify different, in the manifest, different properties for your models, and be able to verify what data it was trained from, who it came from, and if it was retrained on any special data. That is one. And I think you also heard about this second one, which is there is a lot of work happening in the software supply chain, because we again want to be able to trace the origin of the software and the provenance of the software. And the question is, can we take those learnings and apply those to ML pipelines? So those are the two, I would say, the research community as well as the industry as a whole is looking at those two problems. And we really have to solve those two problems to be able to make this a success. Yeah, you can find more information about this at the link here. And I think that was my last slide. Yep. Okay. Any questions? C2PA, yeah, I think this is, like I mentioned, they actually have this idea of, so historically, you know, the content origination was really important. So I think C2PA has this where you can, when you take a picture from a camera, if the camera is C2PA enabled, it will put a signature in it. And then as if that picture is modified, that signature won't be valid. And so if you're using that, I think there is integration with Adobe and Creator and all of that. So there is this lot of work happening in the media space, right? Where you put signatures and you verify signatures and metadata. And now they are saying, hey, we have done all this work. It is very similar to, can we apply when you create a model? You can actually put like a hash of all the data that the model was trained on. For example, I don't know, a license for the model and some other things. And again, create a manifest. And then again, that can be verified. And every time you retrain, you again update. So create a chain of trust. But they already have a really nice system in place. But they are specifically, there's a white paper out there. I think if you go look, c2pa.org. And we are also doing work at Intel to apply this to the model pipeline. Because I think that is really a big problem, because you have all these models and you think you're talking to ChatGPT and you're not really sure. So can we apply things like confidential computing, for example? You can do verification, but just verifying a hash is just doesn't really tell you much, which means you can now look at, not only verify the hash, but you can go, or verify the signature, but you can now go look at the manifest and actually verify some additional properties of the model. Because that, I think, is the biggest issue. While we talk a lot about attestation, everybody is just creating these blobs of hashes, and it's just not scalable. So see, this idea of using a manifest is a good direction. I guess one of the directions. I think there was another paper that was shown. Microsoft is taking a slightly different direction around, I guess, an open source blockchain service about the attestation. Yeah. Any other questions? I think there's someone in the.
In the NVIDIA, the Grace Hopper architecture, you have an NV-link between the ARM and the GPU. Is that right? So what is the equivalent of that in the TDX?
So with H100, it's the same, right? Today you have no secure link actually between the TDs and the GPU. You can create this bounce buffer in this untrusted memory. So you create this area of the memory and you encrypt everything that goes in that, and then you decrypt it on the GPU side. And that's what I say as a phase one here, right? It is all going over PCI. It's you have to, but this is very expensive if you have to encrypt all the traffic that goes between the devices. And that's where, for secure DMA, we have the TDISP and SPDM protocols. And that will come in the next generation of all the hardware, I would say, both on the CPU and the GPU side.
Yes, so Antoine Deligna from Microsoft. So you mentioned the software supply chain and verification and trust in code. So what's Intel's ideas or work that you have done in this space to solve that problem?
So we have some people from our lab who are participating in OpenSSF. I think there is, and then we are just beginning to look at it. I believe there's a group of people. I'm not sure if Microsoft is involved. I think there are people from Meta and Google who are through OpenSSF looking at looking at the techniques from software supply chain to be applied to AI pipeline, because some of those won't directly map. And I think we heard this morning, Nelly mentioned this, where software supply chain, secure software supply chain is quite advanced. You can do builds in these enclaves, right? When you're doing a build, and you can actually verify the build was done in a trusted way and then can you now take the same things and apply when you are doing the model training and such. Because there is a lot of software involved, right, when you are running this set of things. So we are trying to actually work through industry groups, because nobody can do this in isolation anyway, right? Because that won't be scalable.